Welcome to this presentation in the course Development Project Construction. Today we're going to talk about the effect of stress redistribution on rockfalls at LKAB's underground mine. My name is Linus Johnsson and together with me is Victor Lönnies. The case which we have studied is a rockfall which occurred on the 25th of December 2014. The rockfall occurred in a footwall drift on level 1020 near the Kirunavaara ore body. Approximately 720 cubic meters of rock fell down into the drift. The same evening there were two seismic events which were recorded. The first one being of magnitude 1.9 and the second one of magnitude 0.5. To examine this problem, it was decided that numerical modeling should be used. There are two theories behind the mechanism of the failure. The first one being unclamping caused by stress redistribution, and the second one being the dynamic events which were recorded that same evening. A parameter study on the joint friction angle was conducted to see how it affects the wedge stability. We will use three different softwares to analyze this rockfall. The first one is Rock and Soil 2, developed by Rock Science. Second one is UDEC, developed by Tekniska Consulting, and the third one is Unwedge, developed by Rock Science as well. In Rock and Soil 2 we will use global local modeling. The global model consists of the entire ore body together with the ground surface, and it can be seen up to your right. It is set up in stages in order to simulate the mining process. Ore is being removed from the ore body, and behind the ore the hanging wall collapses and backfills the void. We will also place a data node on the 1020 level in order to record stresses for the different stages, which will then be inserted into the local model. The local model, as seen down to your right, consists of the footwall drift. We have added joint sets in order to simulate the wedge. Both models will be simulated plastic and elastic, and the results will be compared between them. There are limitations in Rock and Soil 2. The software does not have any memory between the different stages computed. If there are a lot of failed elements in stage 1 where level 960 is being excavated, and then you move on to the next stage, which is excavation of level 990, the software does not remember the previously failed elements, and this might affect the results. Rock and Soil 2 uses the finite element method. It does not allow for separation of elements, and therefore the wedge cannot slide into the drift. Unwedge was used to get a calculated factor of safety on the wedge which fell out. The software is easy to use. We just define dimensions and directions of the drift. We then add joint sets which were acquired from LKAB and then define joint parameters. In the picture to the right is a 3D visualization of the wedge.
We made three types of models in UDEC. The first model, we called it static. In it, there's no history of mining, we were just adding the current stresses. The second model, we called it continuous. In it, we changed the stresses to reproduce the sequence of mining. The final model is a static model with no history, but we add a dynamic wave on the left boundary. The static and continuous model can be seen to the right, and the dynamic loading model can be seen at the bottom to the left. For each model we also made a few attempts with a fractured wedge. We fractured the wedge by adding joints inside the wedge with a spacing of 0.5 meters.
And time for results. In Rock and Soil 2 we saw a small shear displacement of a couple centimeters or millimeters along the joint in all models, both plastic and elastic, and for all stress fields used. As for the dynamic wave, it did not affect the wedge, but further analysis might be required in this area. As I mentioned earlier, there are limitations in the software. The finite element method did not allow the mesh to be deformed, and therefore the wedge cannot slide. Joint failure was observed in all models. A joint failure might be an indication that the wedge is actually moving, but as mentioned, there are limitations in the software. In unwedge, we got a factor of safety of 0.225 with no added stresses. But adding a small isotropic stress field of 1 megapascal, the factor of safety was increased to a value more than 4 and therefore considered stable.
The result from UDEC and the static loading model showed that no wedge slip occurred until the joint friction angle had been reduced to 5 degrees. This happened when mining on the 1080 meter level. For the continuous model, wedge slip occurred before that. It started to occur when joint friction angle had been reduced to 20 degrees on the 1080 meter level, and it also occurred on the 1020 meter level when the joint friction angle had been reduced to 15. As you can see on the pictures in the middle, there are also a lot more yielded elements around the opening for the continuous model, which is the bottom model.
In the dynamic loading, a wedge slip only occurred when the friction angle was reduced to 10 degrees. This was for the level 1050 stress level, and the wave had a velocity of 2.4 meters per second compared to the original 1.2 meters per second. When analyzing the fractured wedge, it was observed that only individual small blocks loosened, but the overall wedge stability was still fine. And time for conclusions. Rock and Soil 2 is not a suitable software for this type of problem. As the mesh is not allowed to detach from each other, it is most difficult to simulate a wedge falling out. In a wedge, because of the high factor of safety, when just adding a small field stress of 1 megapascal, it is most unlikely that a gravitational or structural induced failure occurred. In UDEC we saw the same thing. The dynamic wave did not affect the wedge either, so it was most likely a combination of distressing and dynamic load. Thank you for listening to this presentation.